What's up everybody, my name is Rohak and today we'll be exploring the fascinating linear regression algorithm together. From in-depth explanations to a full Python tutorial, this video is the ultimate beginner's guide to linear regression and I really hope you enjoy it. Well, enough of me talking. Let's cut right to the chase and dive in. Welcome to the programming section of this video, where we'll be putting our understanding of linear regression to the test by implementing it from scratch in Python. Now, if you want to follow along with the tutorial, I'll have a link to the Kaggle dataset containing the data we are about to analyze in the description below. Feel free to check that one out. With that all aside, let's get started. First, we need to import pandas, matplotlib, and seaborn into our notebook. Pandas will be responsible for data frame manipulation, while matplotlib and seaborn will both be used for visualization purposes. Perfect! Now let's import our salary data, which we'll be using throughout the remainder of this tutorial to illustrate linear regression in Python. To do this, we'll create a new data frame, df, and assign it to the result of pd.readCSV, with our CSV file passed in as a parameter. Next, we'll rename our columns for further clarity. Awesome. Now, to see what our dataset looks like, we can call the head method on our newly created dataframe object, which will print the first 5 rows of the CSV file out to the console. So here, if we call our head method and click run, we see that we yield a data frame with 2 features, years of experience and salary, that will be used as our independent and dependent attributes in linear regression. Also, if we want to learn more about our data, we can call the describe method on our data frame. So here, if we click run, we can see that we get a data frame of various metrics regarding our attributes, ranging all the way from the mean value to individual percentiles. Finally, to complete our data pre-processing stage, let's check to see if our dataset has any missing values, which we can easily do by calling the isNull method. So here, if we click run, we see we yield a data frame where each entry represents whether the value is null or not null. So here, if we scroll down, we can see that all of these values are false, which tells us that there are no missing values in our data. Knowing that our data frame contains no missing values and is properly pre-processed, we can finally move on to building our linear regression model. Well, what are we waiting for? Let's get started. The first thing we'll do is model the correlation between work experience, which is our independent variable, and salary, which is our dependent variable. For this, we can apply the scatter method of matplotlib and pass in both attributes as parameters with bracket notation. Awesome! Next, we can add a title and some axes labels to make our plot more readable and easy to follow. So here, as you guys can see, I added some of the graph metadata by calling the title, xLabel, and yLabel functions with string labels, padding, and font size all entered in as parameters. So in order to properly visualize our scatter plot, we can simply call the show method. And if we click run, we can see that we yield a scatter plot with years of experience on the x-axis and salary on the y-axis. But here, it's also important to notice that we see a clear, strong positive correlation between both of the variables. The more experience an employee has, the more likely they are to receive a higher salary. Next, we can use the heatmap function of seaborn to plot the correlation between work experience and salary. So first, we create a correlation object that represents the r-squared value for both of our attributes. Now we can call the heatmap function of seaborn, pass in the correlation object we generated earlier, specify a color map, and set annotations to true so that we can actually see the r-squared values on our heat map. So here, if we click run, we get an awesome heat map. And looking closely at it, we can see that salary and work experience have a 98% correlation coefficient, which is super strong. Now that we've visualized our data and gained a solid understanding of the correlation between our independent and dependent variables, it's time to begin the model building process. So let's jump right in. Now, to begin building our linear regression model, we first need to ensure that we break up our data into training and testing sets. This is done because we want to train our model on a larger subset of the data and test it on a smaller subset of the data that it hasn't seen or encountered before. So to do this, let's first import train test split from scikit-learn's model selection package. Now let's separate our x and y data by assigning x to equal the work experience column and y to equal the salary column. Finally, in our call to train test split, we pass in both pieces of data and specify the test size to be equal to 0.2. When we set the value of our test size to 0.2, what we're really doing is reserving 20% of our data for testing purposes and 80% of our data for training purposes. After this, we can assign the result of the function to 4 parameters representing the training and testing sets for x and y respectively. To confirm the 80 to 20 split we made earlier on, let's check whether the appropriate subset of our dataset corresponds to the length of our training and testing sets. So here, if we click run, we can see that the two match exactly. The length of our training set, which is meant to cover 80% of our data, is equal to 80% of our dataset, and the same pattern follows for our testing set. With that all aside, we can now focus on creating our linear regression object. To do this, we first import linear regression from scikit-learn's linear model package and assign a new variable called classifier to a new linear regression object. Then we can train our classifier by calling the fit method with both x and y training sets passed in as parameters. Here, it's also important to note that we need to call the toFrame method on our x and y training sets to ensure that both of them are two-dimensional and can therefore be used as valid input to the fit function. To make predictions with our linear regression model, we can simply call the predict function on our classifier with the two-dimensional form of the x test set passed in as a parameter. So in order to check whether our predictions have been made, we can simply print out this value, and if I click run, we can see that we get a list of all of the model's predictions on our testing set. Additionally, if we want to find out the slope and y-intercept of our regression line, we can access the coef and intercept fields of our linear regression object, which return both of these values in list form. These are the formal parameters for our regression line's mathematical equation, where m represents the slope and b represents the y-intercept. So here, if we click run, we can see both of these values printed out to the console. Now let's visualize our predicted data points and regression line to see how we match up against the observed values. So first, we can start off by graphing two scatter plots representing the original data and the predicted values. So for our first scatter plot, we simply graph the original data against each other with work experience on the x-axis and salary on the y-axis. But for the second scatter plot, we take all of the x values in our test set and compare them to our model's predictions on the y-axis. To plot our regression line, we can specify the x-test and predictions variables as parameters, specify parameters for color and line width, and see what we get. However, before taking a look at the final plot, let's add some axes labels, a title, and a legend to make our visualization more readable to someone who isn't exactly familiar with the salary data. So here, as you guys can see, I've specified a title with the padding and font size parameters added optionally, and I've also specified a legend on the lower right hand corner of our plot. After a call to plot.show, let's run our code and see what we get. So here, if we click run, we get the following plot and visualization, and here we can clearly see that our regression line models the original data really well. The residual values appear to be minimal, and our line looks to be a great fit for our data. Finally, let's gauge how well our regression model performed. To do this, let's first import the metrics package from scikit-learn. Now we can retrieve the mean squared error by calling the mean absolute error function with our y test set and predictions passed in as parameters. This function will check how well our predictions matched up against the correct y values to measure the sum of squared residuals for our model. After this, we can get the overall performance of our model by calling the score function with our x and y test sets passed in as parameters. This metric represents how well the model explained the data it was tested with. Printing both of these values out to the console, we see that while our mean squared error could definitely be improved, The nearly 95% accuracy measure is definitely a positive reflection on the performance of our model. Well, there we have it. We learned so much about linear regression, its internal function, and its full implementation in Python with the scikit-learn library. If you still have doubts or lingering questions regarding the script, the description contains a GitHub link where you can access the full Jupyter notebook that we used for this tutorial. If you enjoyed, don't forget to like and subscribe for more content just like this. Thank you so much for watching, take care, and I'll see you in the next one.